Hello everybody, Assalamu alaikum. My name is Syed Shahmir Faraz. I am an electrical engineering student at Habib University and I am currently enrolled in my third year. This is my case study for my course of electrical machines, and the case study topic that I chose for this course was permanent magnet synchronous motors and their emerging applications. So let's start. First of all, what are permanent magnet synchronous motors or PMSMs? What they are basically motors which use permanent magnets. But these permanent magnets are attached to the rotor, which is the rotating part of the motor, and they produce a permanent magnetic field. Whereas the stator, which is the stationary part of the motor, is connected to an AC supply and it produces a rotating magnetic field. Okay, so what is the need for PMSMs? We already know that we have a lot of motors around us, like an induction motor and many more synchronous motors as well. So why do we need PMSMs? So PMSMs have their own advantages and that is why they are used. They first of all they do not require a DC supply at the rotor like their other synchronous motors because of the permanent magnets. Also, according to studies, PMSM motors are approximately 2% more efficient than a highly efficient induction motor. Now, this 2% is very much when you compare it to applications, and that is why the PMSMs also have the best performance as compared to all other motors in terms of electrical efficiency and the torque density. Another advantage of the PMSM is that they also safeguard against the demagnetizing armature reaction field, hence there is no need for a magnetic fastening process. Moving on, the design of the PMSMs. The design of a PMSM is basically the stator and the rotor, which is the rotor which is the rotationary part, and stator which is the stationary part. So we can see the rotor at the top of the diagram where there can be seen the magnets on the sides as well. The rotor hub is shown and the stator is shown at the bottom where it is surrounded by bar wound wire. The rotor core sections can also be seen alongside the bearing support assembly. So this diagram is pretty simple and self-explanatory and tells us how the motor is assembled. Moving on. So the rotor comprises of the permanent magnets, and these permanent magnets have to be of a special quality, which means they must have a high magnetic flux density, otherwise the PMSM won't be as efficient as we want it to be. A PMSM can be divided into two categories depending on the rotor design. These are a surface permanent magnet synchronous motor or an SPMSM, where the magnets are at the surface of the rotor, or the other is the interior permanent magnet synchronous motor or the IPMSM, where the magnets are inside the interior of the uh, rotor. These can be shown on the figure. On the left we have the SPMSM and the magnets in orange can be shown on the surface, while on the right we have the IPMSM where the magnets can be seen inside the surface. So the difference between the two types of motors is that the SPMSM, although it allows a high air gap flux, but it has a low structural integrity and a low mechanical strength. Hence, it is used for low speed applications. And another advantage is that they have a high power density due to the radial flux. The radial flux will be discussed later on. For now, the interior PMSM, the IPMSM, is much more difficult to build than the SPMSM. The IPMSM is stronger and thus it is used for applications which require a higher speed. The stator is designed like it has a common design where it has an outer frame and a core with windings. Apart from that, the stator design is also comes with 2 and 3 phase windings. Moving on, what is the working principles of the PMSMs? The working principle of the PMSM is that the rotating magnetic field of the stator interacts with the constant magnetic field of the rotor. What happens is that the rotating magnetic field interacts with the permanent magnetic field, and thus via Ampere's law the torque is produced. Not via Ampere's law, according to Ampere's law, torque is produced, and that torque allows the rotor to rotate. As the rotor rotates in harmony with the stator, the synchronous speed is generated. However, this speed is not enough to start the PMSM itself. Thus, we use techniques to start the PMSM. One such technique can be using the squirrel cage motor to start the PMSM itself. Moving on, there are two types of PMSMs, a radial field PMSM and an axial field PMSM. In a radial field PMSM, the radial field flux is along the radius of the machine, and this type is most commonly used, while the axial field flux is parallel to the shaft of the rotor, and these type of PMSMs possess high power density and quick acceleration. Moving on. Like other machines, PMSMs also require control, and these controls depend on the different applications of the PMSM. The PMSM control techniques are shown in this table. However, they are divided into two main categories, a sinusoidal and a trapezoidal. They are shown in the table below as well. Moving on. So now this is the important part of the presentation, which includes the current work on the PMSMs. So for this I went through three research papers in which I gathered different applications, and these I have summarized over here for you. A direct driven IPMSM for a full electric sports car. For this, the authors suggested that they should use an IPMSM motor for a full electric sports car. The problem with electric sports cars is that they require maximum torque at low speed due to absence of gears, and this IPMSM can provide that to them. As a result, the authors conducted experiments, and after the experiments they found out that the need for the required torque as well as the required current is fulfilled by the motor alongside a vast range of speed, which is absolutely perfect for a sports car. So this hypothesis was actually proved, and this is an exciting new idea for the IPMSM. Moving on to the second application, analysis and design of a 300 watt 500,000 RPM slotless self-bearing permanent magnet motor. For this, the idea presented was to build a very high speed electrical machine drive. This is a very important proposal with regards to future applications which may require very high speed drives. And for this, the authors have proposed specific designs in which the rotor should be ironless and the stator should be uh, slotless. Okay, for this, the authors built their own prototype according to the structures, and when they tested those structures, so the machine drive produced high speeds and frequencies recording up to 505,000 rpm and a frequency of 1 megahertz, which is a lot. And this is another exciting thing for the future. It can be used in many applications such as centrifuging machines and many more. Moving on to the last application, transverse flux type cylindrical synchronous motor using generic armature cores for rotary machinery. In this paper, the idea proposed and executed is for a linear PMSM. Thus, they are combining a linear motor and a permanent magnet motor. Specifically, this motor is the transverse flux type cylindrical linear synchronous motor, which uses armature control for rotational machinery, and it is mainly used to address the problems related to transverse flux topology. The experiment was carried out after the authors that proposed the changes. They designed the experiment and they monitored it, the thrust density and the Cognitive force as a simulation first, and then the structural hypothesis was also carried out and it was validated after the 3D prototype was tested. After comparison with the few motors that are already in the market, it was proved that this motor is right up there to the mark, and it can be used as a linear PMSM for transverse flux type topology. Thank you. These are the references that I've used for my